So, good evening everyone. Welcome to Shaurav's classes. Hope you all are fine. So today we have chosen the topic of the video as tomato problem solving session, the subjective portion. So tomato here is the famous book Test of Mathematics at the 10+2 level that is published by Indian Statistical Institute, East-West Press. Every I.S.I. CMI aspirant must necessarily contain this book. You can easily buy this book at concession prices on Amazon and Flipkart. So in this book there is a bunch of problems including the past year papers and other bunch of problems that were set by I.S.I. professors who thought that what were the essential needs for a student to cater to I.S.I. entrance examination. And the problems are divided into two parts, the subjective section and the objective section. The problems range to vast varieties from school maths to your maths up to class 12, calculus, algebra, to low school maths such as unitary methods, ratio, proportion. So in I.S.I. general mixed type problems are usually asked as that's their hot favorite because they believe or what they test actually in a student is the mathematical aptitude of the student. So the mathematical aptitude of the student is tested on basis of the question paper. So for getting into the I.S.I, so you need a mathematical aptitude and a problem solving attitude in your life. So you must try problems by your hand, you must try problems by your own self so that you can get into more practice. And here I'll give you some sample problems from the I.S.I. past year papers, from I.S.I. test of mathematics at the 10+2 level, abbreviated as tomato by the users. So here we will discuss some core topics and concepts which I believe will help you further to solve problems in future. So here is our first problem for the day. Find the number of onto functions from this set 1, 2, 3, 4, 5, 6 to 1, 2, 3, 4, 5. Now finding number of onto functions was a very hot topic and many students face difficulties in understanding this concept. So I just want to start with this problem so that I could explain you the concept with more clarity. So I request every one of you to just take a pen and paper and try this problem for a few moments. So the stipulated time meant for this problem is over. So many of you could solve this problem. So it's their advantage. And if you cannot solve this problem, don't be disheartened. It is because this is one of the most, I must say, hot problems that come in I.S.I. and this is very difficult if you don't understand the concept. So once you get into the concept, you will be able to get this very clearly. So now we are starting to solve the problem, so please check it clearly. Now, I want to ask you, what do you exactly mean by an onto function? What is an onto function? An onto function is a function which says that for every element in the range of the function, there must exist a pre-image in the domain of the function. So I hope that these technical terms are not very clear to you. So whenever I write a function f, so functions are usually denoted by f. So this function f is usually defined from set 1 to set 2, where set 1 has some elements and set 2 has some elements. Okay. So this set 1 is known as the codomain of f. This set 1 is known as the domain of f, and this set 2 is known as the codomain of f. So this set 1 is known as the domain of f, and this set 2 is known as the codomain of f. Now I want to tell you that set 1 contains some elements and set 2 contains some elements. Then what does this relation basically mean? This relation means that there is a mapping from set 1 to set 2 following the conditions that one element in set 1 maps with not more than one element in set 2. Okay, so one element with set 1 must map with one element in S2. It means that if x belongs to S1, then f of x equals to y1 and f of x equals y2. So f is a mapping, as I have said, implies y1 equals to y2. So if and then y1 equal to y2. So if this takes place, then that is called a functional mapping, or that mapping is known as a function. Now what is an onto function? An onto function is, you have understood that every element of S1 must be mapped with at least one element of S2. An onto function is a special type of function in which every element of S2 has been mapped with at least one element of S1. So we are seeing S2. So for S2 there exists at least one element whose map is in S2. So in every element it occurs. So that is called an onto function. Okay. So our problem is to count how many onto functions are from a set with number of elements n to a set with number of elements r. So this is our work, that I need to calculate number of elements. Now of course you can see that if r greater than n, then f is not onto. You can very clearly see this. This is because if r greater than n, then there exists some elements which are not mapped, and hence it cannot happen. So for onto function, r must always be less than equals to n. For onto function, r must be less than equals to n. This is the main criteria for onto function, which will be utilized throughout the problem that we are going to solve. Okay. So we are generalizing the case of finding the number of onto functions, and I believe that you can solve the particular case thereafter from there. Okay. So now we need to count that how many functions are onto. So let this set be S1. And let this set be S2. So the elements of S1 are A1, A2, A3, are elements are there in S1, and in S2, A1, A2, A3. So I name it B1. Bn elements in S2. So the problem of finding number of onto functions is basically finding the number of onto maps. The mapping is onto. So for B1 there must exist an AI, at least one AI, as I said. More than one might be possible, but there must exist at least one. For B2 it's the same case, for B3 is the same case, and up to Bn it's the same case. Now I want to show you that. So let me adjust the camera a bit so that you can see the entire picture properly. So this is the representation that we will use. Now, first of all we will determine that what is the number of functions that is possible from S1 to S2. So what is the number of functions? So A1 must go to some n values. So A1 must go to some n values. So first choice for A1 is n times. So what we are finding is number of functions. So I hope that you cannot see it. So what we are basically finding is number of functions. Okay, so number of functions. For 1 there is n choices, for 2 there is n choices, for A3 there is n choices, up to for AR there is n choices for R terms, which is nothing but n to the power of R. So this is the total number of functions. Now of course from the total functions all cannot be onto, all the functions cannot be onto. Therefore some functions from here are not onto. So we need to subtract that. Now how do we do that? Now forget all this and let's get back to a very well-known principle which we call as the principle of inclusion and exclusion. So inclusion and exclusion is a very well-known technique which is also known as the sieve technique. Inclusion and exclusion or sieve technique. So now we will discuss about the inclusion and exclusion of the sieve technique. So what does the technique say? It says that suppose you have 3 sets. So I am drawing in terms of Venn diagram so that you all can understand. And it says that suppose this set S1, this set is S2, this set is S3. Now this set has N1 elements, this set has N2 elements, this set has N3 elements. Okay, it is given that this is there. So it is required to find that what is the total number of elements collectively in all these 3 sets. Now it might appear to you that the answer is N1 plus N2 plus N3. But no, the answer is not N1 plus N2 plus N3. Why? Let's check how. In N1, I can name this small portion as K1, this portion as K2, and this portion as K3. So these three portions are included in N1 also. But you see that these three portions, this portion is also included in N2, this portion is also included in N3. But those portions were counted twice or thrice. But we need to count it at least one. Right? This is because we cannot count, that will be an overcounting problem. We will overcount things which will lead to error of the result. So we need to subtract what is needed and what is not needed. And that's why it is known as the inclusion or exclusion of the sieve technique. Why the sieve technique? We have seen that when grains or when say rice, that raw rice from the fields that comes, what we do is we take the sieve that has small holes in it and we just shake it. What happens? The thing that is required, it remains and the rest falls out. That is basically inclusion and exclusion. The proverb that you need to remember for the shortcut trick is include what is needed, exclude what is not. It says that only include those things which are needed. Don't include extra terms from there. Okay? So what I will do in case of calculating what is the total number of elements in all the three sets, I will include all these. S1 plus S2 plus S3. So this is needed. So we include it. So include what is needed, exclude what is not needed. In this we have counted the intersection terms, but oh no, we have just missed this small portion in the center. So include what is needed, exclude what is not needed, and then again include what is needed. So this is the principle in inclusion and exclusion, that is for three sets. Now we can easily generalize it to n number of sets if we have. So what the inclusion and exclusion principle will look like for n sets or the sieve technique? So if we have sets S1, S2, S3 up to index up to Sn, then include what is needed. So this was included. Exclude what is not needed. Again, include what is needed. Exclude what is not needed. And it goes like this. So what did I teach you, friends? We have learned that in the principle of exclusion, the inclusion exclusion, that is very simple. It's highly simple. We need to include what's needed and exclude what's not needed in our problem. And I will apply this same method to count the number of onto functions. Okay? So let's see. So we can see that if the number of onto functions from say S1 set whose cardinality is n to S2 set whose cardinality is r. So what is the total number of functions? So for this is r to the power of n. Now for onto functions everything should have at least one map. Now imagine you have n balls and r boxes. Now you need to place those n balls in r boxes. How many ways will you do it? That is the question. So what you do is you can keep any box empty. That is the condition that is given. So what you do is, you select a box out of those and make that empty. You select a box out of n, R boxes you select. So you select a box, it's not NCR. So R boxes, since it is, so it's RC1. So it's RC1. So you select one box. So what did I do? I just selected a single box. So you select one box and you make it empty. In the sense you make it empty means other box have to be filled. So in how many ways can the other box be filled? The number of ways in which the number of functions exist. But one box is out. So what is the number of functions now? R minus 1 whole to the power n. So include what is needed. The number of total functions is included minus one box is empty. That doesn't form an onto function. That is excluded. But oh no, we have missed out in this process. If two boxes are left empty, those we need to write. So include what's needed, exclude what's not needed. Again, include. So it will be n minus 1. Again, include what's needed. Okay. So in RC1 ways we have choose, and the number of functions is this, R minus 1 C1. Again in RC2 ways we have choose, and the number of functions in this case is RC2 into n minus 2. But again, we have also counted in which the number of ways 3 boxes are left emptied. But that doesn't form an onto function. So again we get back to the same principle. Include what's needed, exclude what's not needed, includes what needed. Then again you need to exclude what's not needed. And so on up till the nth term. So I hope that this concept is very clear to you. This states that include what's needed, exclude what's not needed. That is basically, that lies in the principle of inclusion and exclusion, and that is the basic principle in which you can solve this problem. So I taught you a very important technique. This is known as the sieve technique to solve problems, and I hope that you will utilize this technique later in solving problems from your own life. So now let's get to the second problem of today's session. So I hope that there will be no problems in number of inclusion and exclusion. This is because all of these depends upon the sieve method. So the next problem of today's class is, if AI is an increasing sequence of positive reals, remember that all AIs are positive reals, then you need to prove that Px, the polynomial Px, which is AI by AI minus x for summation of I equals to 1 to n equals to 2015, has n real roots. So you need to prove that this equation has n real roots. And I give you some stipulated time to solve the problem and think it of your own. So the question says that if you have an increasing sequence, that is, and this is generally the notation of a sequence notation. So then this equation has n real roots. So I give you some stipulated time to solve the problem. Please try it. Okay, so the stipulated time given for this problem is over, and now I just tend not to solve the problem. So if any of you have solved, then please tally it with your answers, and if none of you haven't, then just see the technique which I used to solve this problem. The method I will use is popularly known as the method of contradiction. So there are many types of proof techniques in mathematics that we use. The proof techniques are, number one, the direct method, that is applying some direct principles or theorems. The method of contradiction. So how does the method of contradiction works? The method of contradiction works in a way that suppose you have a statement to prove and you assume the negation of the statement. So if you assume the negation of the statement, so suppose that the statement given is false, so the negation is true, and you assume just go mathematically by mathematical steps and conclude a thing which is wrong. Now the thing might be a universal truth, might be anything, but that thing is surely wrong, decided. In that case, you must say that your assumption was wrong. Hence, the negation of the negation was true, which is the statement was true. So, we will use exactly this principle to solve this question. So, what was the coefficients, the equation? So, this was our equation. So what does the problem say? We need to prove that these has n real roots and ai are positive reals. So what do we assume? That there are at least two complex roots, because complex roots occur in conjugate pairs. So we assume the contradiction that there are two complex roots which are arrived in conjugate pairs, alpha plus I beta and alpha minus I beta, where beta not equals to 0 is very important. Because if beta equals to 0, then this no longer remains a complex number but turns into a real number. So what I do is that since this is a root, this should satisfy the equation. So name this equation 1, and since its conjugate is also a root, so I will just shift the board so that you can just see it very clearly. And since the conjugate is a root, so A1 Now when I subtract these equations 1 and 2, what do I get? So what I get is, so let me subtract this. Subtracting I get, so if I take A1 common, in the inside I get and terms like this, and the down term what it becomes? It becomes A1 square minus A1 into alpha minus iota beta minus A1. So A1 square, A1 into alpha plus iota beta plus alpha square plus beta square. So this is what I get, and same for every term, and the right side becomes 0. Okay. So you see that this inside number, if I just multiply, then it is just 2 iota beta, because the alphas get cancelled, and this term cancels out, and I get ai square plus alpha square plus beta square equals to 0 for all I. So I am replacing it by general I. Now just observe that this term is positive, this term is positive, ai are given positive in the question. So then, but the product is 0. Then which term must be 0? Then beta is the only thing which must be 0. But we have assumed that beta not equals to 0 in the beginning of the question. And hence, this is the contradiction which leads us to believe that our statement was wrong. And this equation contains exactly n real roots. So I request you to see this problem once more so that you can get a clear understanding. So what I did was just I assumed the contradiction and then I just subtracted the equations. So today in this video session we have learned two very important concepts. The sieve principle, the function, the method of inclusion and exclusion, and the method of contradiction. So these are very important as far as your exams regarding I.S.I and CMI are concerned. And of course these techniques are, the problems based on these techniques are present in plenty in Tomato and plenty in Shorev's classes study materials. So you need to grasp those classes study materials and these concepts to get a very maximum achievement result in Indian Statistical Institute. So all the best for your future and your exams. Hope you will give and clear it safely. For now, thank you and goodbye.